looked at part-of-speech tagging in another lecture. Now we want to look at the standard algorithms that are used for POS tagging. A quote from Gemini: "Part-of-speech tagging acts like a linguistic GPS for words in a sentence. It assigns grammatical labels like noun, verb, adjective, or adverb to each word. This helps computers understand the structure and meaning of a sentence. With POS tags, a machine translation system can translate more accurately, or a sentiment analysis tool can determine if a sentence expresses positive or negative emotions." The part-of-speech tagging algorithms that we'll look at include HMM, CRF, perceptron, decision trees, RNNs and transformers, and LLMs. This table, created by Gemini, lists and describes some common algorithms used for part-of-speech tagging. The first algorithm is hidden Markov model, and this is commonly used with the Viterbi algorithm. This model uses statistical probabilities of word sequences and part-of-speech transitions. It employs the Viterbi algorithm to find the most likely tagged sequence. This is an efficient algorithm which handles ambiguities well, but it has limited feature representation and struggles with rare words. Next is the conditional random fields or maximum entropy Markov models. These are similar to HMMs but can incorporate more complex features, including things like word prefixes, suffixes, and the surrounding tags. This becomes more accurate than HMMs as it handles overlapping features well, but the training can be slower. So there's always a trade-off there with your advantages and disadvantages. Perceptron algorithms iteratively update weights based on misclassified examples. This is similar to support vector machines. These can be efficient for smaller datasets, but they can be slow on large datasets and may not converge to an optimal solution. Decision trees classify words based on a tree structure with decision rules at each node. This is fast and interpretable results, but it's less accurate than statistical models for complex datasets. Neural sequence models such as RNNs, or recurrent neural networks, or transformers, utilize the deep learning model to learn long-range dependencies and contextual information within sentences. These are highly accurate and can capture complex relationships between words. However, they are computationally expensive for training and require large data sets. Fortunately, we have large language models, like BERT, for example, and they can be fine-tuned for this purpose. Here we use pre-trained transformer models and then fine-tune them for the specific task of part-of-speech tagging, which leverages the ability of the large language model to understand the language context. This advantage includes state-of-the-art accuracy, so this is powerful for complex tasks. However, it does require significant computational resources, and of course there's a potential for bias from the pre-trained model. To look at the performance of POS tagging in general, there are a lot of ways to measure accuracy, but if we take the simplest form and measure accuracy as the percentage of words that were correctly tagged, when we're using state-of-the-art models and high-quality annotated data sets to train them on, we can achieve accuracies in the 96 to 98% range. Of course, performance of POS tagging can vary depending on several factors, and those include the choice of algorithm. So we covered some different algorithms and their inherent strengths and weaknesses. Generally, simpler models like the HMMs are faster but less accurate, while complex models like neural networks can achieve higher accuracy but require more computational resources and data. So there's always a cost in that trade-off. The training data also affects the performance. POS taggers that are trained on large data sets of quality pre-tagged text are going to perform better than those that are not. So the higher the data quality in terms of its consistency and accuracy of the tags in the training data will determine the level of performance you can achieve. Language complexity also contributes. When we have a language that has a rich morphology, such as a lot of variations on word forms or any complex syntax, these can pose challenges for part-of-speech taggers. And then there's ambiguities. If there are a lot of words in the test data set that can have multiple meanings, for example, words that can be nouns or verbs, then this inherent ambiguity in the language itself is going to lead to errors in the tagging, which of course is going to affect the performance score. That is an overview of the algorithms that are standard algorithms that are used for part-of-speech tagging today.